Hi, in this section, we're going to start reinforcement learning. And we'll have a fairly long section on reinforcement learning, and then we'll, in the next section, get to AlphaGo and AlphaZero, which I find very exciting. You can take a whole course in reinforcement learning. So this is going to be a really fast crash course. So what is reinforcement learning? So reinforcement learning is all about learning to take actions where the actions have consequences. So the idea is that one is always in an environment, a state, and we can select actions, make sequential decisions, and these sequential decisions change the state. And then we're going to get reward if we reach desirable states. So that's the high-level technical definition. So board games, Go or chess, right? We have to select moves. And if you think of your opponent as just some automaton, your moves affect your reward, whether you win the game. We're going to talk about Atari games, not this unit, but soon, because Atari games were used as a benchmark early on, well, early on meaning 5 years ago. Robot control, self-driving cars are an example of reinforcement learning. Dialogue, what we say to each other matters, right? It has consequences. So just choosing what to say can be viewed as a reinforcement learning problem. Life is a process of sequential decision making. People take this fairly seriously. Rich Sutton, who I worked with for a long time, really believes that this is the right way to formulate, the game of life. So now we're going to start getting a little bit more mathematical. So policies. A policy is a way of behaving. It's a function that takes a state and selects what action to take in that state. Except we're going to treat that function not as a deterministic function, but as a probability distribution. So it's okay if your policy is stochastic, meaning you don't always make a deterministic decision in the state. You can flip coins to decide what to do. So a policy is a probability distribution over what action one is going to take in a given state. And I'm going to write that as the probability of an action. So I'm letting pi denote the policy. Pi is a policy, assigns a probability to an action in a given state. And this policy is under the agent's control, right? The agent is deciding what to do. I wrote a blog post on free will and when choices exist, but this is the mathematical framework of having a choice. Now, the simplest way to learn a policy, to learn what actions to take, is to imitate. And this is called imitation learning. So we can imagine having a large database, like Tesla is collecting data from drivers. So they've got a large database of their sensors, their cameras, that define a kind of state and what action the driver took, the steering wheel, the gas pedal, the brake. But at a very abstract level, I want to imagine having a huge set of pairs of what state an expert was in and what action the expert took. And now I want to learn to imitate the expert. And the imitation of the expert, that learning process can be parameterized in terms of cross entropy. So basically what we want to do is predict the action from the state. So we're going to just treat this as a prediction problem, right? You think of the action as a label for this, and we're just going to do label learning, right? We're going to learn to predict the label from the state, and it's just cross entropy. So if there's some deep network that's taking this state and selecting this action, then we're going to minimize the expectation over drawing pairs from our training set, or maybe from the expert's population distribution, of minus log the probability of what the expert did given the state. This is straight up standard cross entropy imitation learning. So this is the simplest way to learn. And this is a central and important concept in reinforcement learning, imitation learning. Now, imitation learning is what's called off policy. So there's two phrases to remember. One is imitation learning and the other is off policy. And that means that the policy that you learn here is probably not exactly the expert's policy. And especially as you're learning, the actions that are being specified by the policy you're learning will be somewhat different from those of the expert. And what that means is that those differences can accumulate over time so that the distribution on states that you're encountering is not the same as the distribution on states that the expert encountered, because the expert steered the system very subtly into good states. And if you haven't learned the expert perfectly, that steering into good states is going to be a little bit misguided and you're going to steer into bad states. So imitating experts is dangerous, right? If you imagine a fire eater or something and you look at them and you try to imitate them, but you don't get it quite right, you're going to get burned. And it's all another issue with imitation learning is it's difficult to exceed the expert performance. You can imitate the expert, but ideally in Alpha 0 and Alpha Go, we get this enormous superhuman behavior, something the experts could not do. And you're not going to get that just from imitation learning. Okay, now we're going to get more mathematical. More mathematical about the formulating the problem of reinforcement learning. So we're going to talk about Markov decision processes. So a Markov decision process is a model of the world, really. So it consists of a set of states, a set of allowed actions, and a next state probability, a transition probability distribution. So if I'm in a state and I pick an action, there's a probability of distribution over the next state that action leads to. And that can be stochastic, right? The world can have randomness in it so that when I'm in a state, take an action, there's a distribution over the next state. So I'm going to introduce the following notation. I'm going to write ST for the state that I'm in at time t. And I'm going to write AT for the action that I take at time t. And then I'm going to assume that there's a reward. This is the thing that I'm trying to maximize, how, my utility. I really should call this a utility. And the reward function is going to be a function of both the state and the action. And that's technically convenient. This is a little confusing. Most people would think that the reward is a function of the state, right? How good is the state? But this way, if I make it both, it handles or it models the case where the action can have a cost. So when I take an action, the action has a cost. It leads to a state that has a reward, but I can summarize that as a reward in the state and the action. And I've already talked about the transition probability. So this is the probability distribution over the next state given the current state and the action. So this defines a Markov decision process. It consists of the set of states, the set of actions, and the transition probabilities, and a reward function. Okay, so we would like to optimize reward. We would like to learn how to take actions that lead to good reward. So at some level, there's this trivial definition of the best policy, right? This is what we're really trying to learn, is the policy. And the best policy is just the policy that maximizes the reward. Trivial, right? However, unfortunately, there are different ways to define the reward that a policy achieves. And maybe the simplest is what's called episodic reward. So the idea here is that there are episodes, like in the game of Go, any board game. You play the game, you either win or lose. That is an episode. So you divide your actions, your life, into these episodes, and you're looking at the reward within each episode. So assuming that capital T is the duration of the episode, then an episodic reward, the reward of a policy is just the expectation over running that policy. Remember, the policy is stochastic and the state transitions are stochastic. So I'm going to take the expectation when I run the policy of the sum over the episode of the reward at that time in the episode. Okay, discounted reward Discounted reward is what's used in finance. You say, well, because of so much uncertainty in the future, I'm going to discount my expected reward in the future. So, and there's a discount rate. As you go into the future, you're less and less confident about what's going to happen there. So you put less weight on on the expectation of the reward in the future and it gets exponentially smaller as you go in time. So here's the formal definition. It's the expectation over running the policy of an infinite sum over all time of the rewards at that time, but the rewards get weighted exponentially in time. So gamma is between 0 and 1 and is strictly less than 1. So that even if this was a maximum reward, this would be a geometric series that has a finite sum. So assuming this has a maximum reward, this will always be finite. This infinite sum will always be finite. Another way to think about this is there's sort of a, 1 minus gamma is the probability of death. And if you die, then you don't get any reward in the future. I don't like that interpretation, but it's a natural interpretation. So there's some probability of death at every time step. Then there's asymptotic average reward. So this is assuming your life just goes on forever. And what you care about is the average reward over forever, right? So this is, if there's a mixing time, then this average reward is kind of a meaningful thing throughout this infinite passage of time. But you can define it formally as a limit of your time horizon going to infinity. Of the average, so you're going to take a particular time horizon. You're going to take the limit as that horizon goes to infinity. But for a particular time horizon, there's the average reward over that time horizon. So that's the same as the episodic sum, except that you're dividing by the time, so that it's a reward per step, right? And this is the asymptotic, meaning as t goes to infinity, average reward, the reward per step. So it's kind of unfortunate that there are these different definitions of the reward of a policy. We're going to focus on the discounted version. And this is common in the literature. Everybody does the discounted version. So okay, so now I'm going to do a little bit more mathematics. If I've got a given policy, pi, this does not have to be the optimal policy. For any policy pi, I'm going to define the value of a state under that policy pi to be the expectation over acting by that policy of the discounted reward given I start in that state. So for each state, and now eventually I'm going to assume that there's a finite number of states. This is a really unrealistic assumption, but it justifies simple algorithms that you'll always see in a course on reinforcement learning. So start thinking in terms of a finite number of states. For any given state, there's the expected discounted reward I'm going to get if I start in that state. So it's a function of the start state. And for a given state, I can define the best value of that state. What's the best value of that state? Well, it's the soup over all policies, the max over all policies of the value I could get for that state under that policy. And that looks like it's defined per state, but really there's an optimal policy. So this is the same as saying V star of a state is the value of that state defined this way under the optimal policy. And we'll try to argue for that, prove that. The optimal policy, pi star, this is what we really care about, right? It's finding the way to behave. And just to point out, just to keep in mind, the way to behave is not always maximizing your next reward. It's reaching a state from which I can get good reward, right? So you have to have long-term reinforcement learning. It's all about long-term planning. But long-term means, discounted. So it's not, in the discounted version, it's not infinitely long-term, it's discounted. Okay, so the optimal policy is choosing the state. It's an argmax over states, and what it's maximizing is your immediate gratification, your immediate reward, plus a discount times your expectation over the next state of the best you could do from that next state. Okay, so this the optimal policy is maximizing your immediate reward and the expectation over the next state of the best you could do from that next state. And V star is the argmax, is the max over action of just this expression. Okay, the next thing I want to talk about is what's called value iteration. And this is, again, something that you would see in any course on reinforcement learning. And again, this is going to be well defined, or the simplest way to define this is assuming a finite number of states. So what I'm going to, this is going to be an actual algorithm, and this algorithm has the property that it provably, for a finite number of states, provably converges on the actual optimal value function and the optimal policy. Okay, so how does this work? I'm going to initialize a value function. Remember, a value function is a function of states, and I'm going to initialize that to be 0. Okay, so initially we'll say all states are worth nothing. But then I can say, well, I'm going to define a next value function that assigns the value to state S, which is the max over actions of the immediate reward plus a discount of the expected future reward, where this is I plus 1. I should have made that in red, and this is I. So when you take this max, you're using the value function you already computed, right? Which is initially 0. So you're taking something that you already know here, and you're optimizing your action at a given state to optimize this, where you're using what you already are estimating for the future state. So if the future state is always 0, if we initialize this to 0, if the future state is always 0, then the next state will just maximize your immediate greedy reward. And if I assume that all rewards are non-negative, which I can do without loss of generality, I can always just take every reward and shift the reward range so that they're all non-negative. If everything's non-negative, then if this is always 0, the next one will be hopefully larger than 0. It certainly won't be less than 0. So the V1 will be greater than or equal to V0. Now, if I make this larger, right, if this goes up at all the states, or at least never goes down, then the next one will be at least as large as this. Then if I replace, let me say it again. If I make this larger, it can only make this larger, right? Making this larger might change the action you take here, but you're guaranteed that by making this larger, you're making this larger. So what that means is that every time I do one of these iterations, I'm replacing this. Every time I do an iteration, I'm getting an old value and a new value for this one. And the new value is always going to make the new value bigger. I don't know if I made that clear. I always have these intuitive arguments, which is the way I understand it, and it doesn't turn it into algebra. So what we get is that every time we get a next state, it's never smaller than the previous state. Whenever we get a next value function at any state, it's never smaller than the value function of the previous state. So if we look at the limit as I goes to infinity, this limit must exist. Furthermore, we're always less than or equal to V star, the optimal value. And then there's this theorem that says that in the limit as I goes to infinity of value iteration, that the limit of the value function is V star. And I have a proof of that theorem. I don't want to get too bogged down in proofs, but let me sort of just go through this at an intuitive level. So I want to prove that the limit this is the limit of the value iteration. And we know this is the best value I can assign to a state, right? So this has to be at least greater than or equal to that. So this is a positive quantity. I want to prove that it's 0, that these are the same. I'm going to do that by a sort of contradiction. I'm going to say, suppose it wasn't 0. Suppose that there was a gap here between this limit and the actual optimum. Well, I can take this expression and just stick in the definitions. The definition of this is the max over actions of using the optimal, when I look at the future rewards using the optimal value function. This is a maximum over actions of looking at the limiting value function. And so this difference is just the difference of these two. Now, I'm picking two actions here, right? An action that maximizes this and an action that maximizes this. If I make this suboptimal, if I make this action the same as that action, this action suboptimal, so it can only go down, right? So replacing this max by whatever's being chosen here will make this go down. But that will make this difference go up. So if I can make these actions the same and it goes up, and that means that if I just require the actions to be the same, it will go up. So it's less than or equal to this, right? Which is the max over A of using the same action in both places. And if I use the same action in both places, then this expression turns into these expressions in terms of the value function. And then what I've shown is that this is equal to a max over states and a max over actions of an expectation of gamma times this difference. And the expectation of gamma times this difference is we're assuming that that is this gap delta. I didn't emphasize that I've defined delta to be the maximum difference over all states. So when I say this is non-zero, I'm defining delta to be the largest possible value it could be. And what I get through this argument is that this delta must be less than or equal to gamma times that delta, because this has pushed the difference into the future. So by pushing this difference into the future, and the only way that delta can be less than or equal to gamma times delta is if delta is 0. All right, so I dragged you through that proof. We're going to continue with more sort of classical standard reinforcement learning in the next unit. So thanks, everybody.